Welcome back to the Deep Dive. Today, we're tackling something pretty fundamental in modern systems, the great architectural compromise, maybe. We live in this world powered by microservices, gives us amazing scalability, independence, great stuff. But that same architecture kind of shattered the old rules of data integrity, the ACD rules we used to rely on. So the challenge really is this. How does a single business thing, like, say, ordering a new phone online, actually complete reliably? I mean, it has to jump across multiple independent services, right? Inventory service, payment service, shipping. Each one is off in its own world, its own database. How do we make sure that whole operation actually works every single time without descending into total data chaos?
Yeah, you've hit the nail on the head. That's the core conflict, isn't it? This database per service pattern, it's basically essential for microservices. It lets them scale, deploy independently. But because everything's separate, that traditional idea of an atomic transaction, all or nothing, instantly it just doesn't work anymore. We simply can't guarantee one single unit of work across all these different networks and services simultaneously. So our mission today really is to unpack the architectural solution that stepped in to fill that gap. We're talking about the Saga pattern.
Okay, the Saga pattern.
Yeah.
But before we get there, maybe we should quickly recap what we lost. ACD, that was the gold standard for decades.
Right. Atomicity, consistency, isolation, durability.
Exactly. But trying to keep all four of those solid across multiple services in a distributed system, well, it's basically impossible, isn't it? Network delays, partitions, they're just a fact of life. These things fundamentally break that assumption of a single central control point. We have to give up that idea of strong, immediate consistency if we want performance.
And that leads us right to the protocol that, just didn't make the cut for microservices. The two-phase commit, or 2PC. 2PC was the traditional way to handle distributed transactions. It tried to deliver that strong consistency using a central coordinator managing a prepare phase and then a commit phase.
But it clashes with how microservices need to work.
Fundamentally, think about the CAP theorem: consistency, availability, partition tolerance. Microservices absolutely prioritize availability and partition tolerance. They need to keep running even if parts of the network are down or slow. 2PC. It goes all in on consistency, often sacrificing the other two, which just doesn't fly in most modern distributed setups.
Okay, so it aims for consistency, but what are the actual downsides? Why did we move away from it, practically speaking?
Well, the biggest one is probably speed and scalability. 2PC is synchronous. It blocks
Blocks what?
resources. During that prepare phase, all the participating services have to lock up the resources involved in the transaction. And this isn't quick. It can take seconds. In any system with decent traffic, that kind of blocking just kills performance. It forces everything to wait to synchronize, which is exactly what microservices try to avoid.
And you mentioned a coordinator. That sounds like a single point of weakness.
Precisely. That central coordinator is a single point of failure. If it crashes, especially after telling services to prepare but before telling them to commit, services can get stuck, locked, they don't know whether to commit or roll back, and resolving that often needs someone to manually intervene. That's just not acceptable for automated, high-volume systems.
Okay, so 2PC is out for most microservice use cases. Too slow, too risky. We need something different. And that brings us back to the Saga pattern. You said it accepts that consistency will happen eventually, not instantly.
Exactly. A Saga, basically, is a sequence of local transactions. Each step in the sequence is just a normal transaction within a single service, updating only its own database. When one local transaction finishes successfully, it then triggers the next step, maybe by publishing an event, maybe by sending a direct command.
So it's like a chain reaction across services.
Kind of, yeah. The whole sequence ensures that the overall business process reaches a consistent state eventually. But, and this is key, it allows for temporary inconsistencies while the Saga is in progress. That trade-off, accepting eventual consistency, is what unlocks the scalability and resilience microservices need.
But if things go wrong halfway through, unlike ACID, there's no automatic rollback, right? This sounds like more work for the developer.
It absolutely is. And that's where the concept of compensating transactions comes in. This is the cornerstone. A compensating transaction isn't magic, it's code the developer has to write. For every step in the Saga that might need to be undone, you need a corresponding compensating action.
Okay, so if a later step fails, say, the payment fails, the compensating transaction has to actively reverse what an earlier step did.
Exactly. It executes logic to undo the effects of a previously completed local transaction. It brings the system back to a consistent state, even if the original goal wasn't fully achieved.
So back to the online order example. Payment fails. The compensating transaction for the inventory service would need to run code to release the items that were reserved earlier. You're basically scripting the undo.
Precisely. It's domain-specific undo logic. And managing this whole process leads to thinking about the Saga lifecycle in specific stages. Typically, you have 3 types of transactions within the Saga. First, you have compensable transactions. These are the initial steps, the ones you design specifically so they can be easily undone by a compensating action if needed.
Like reserving inventory. That can usually be unreserved.
Right. Then, somewhere in the sequence, you often hit the pivot transaction.
The pivot. Sounds important.
It really is. Think of it as the point of no return from a business logic perspective. Once the pivot transaction succeeds, maybe the payment is irrevocably captured or the item is physically shipped. The recovery strategy changes. Before the pivot, if something fails, we try to roll back using compensating actions. After the pivot succeeds, we're committed. The goal shifts to ensuring the rest of the saga completes no matter what.
Okay, so failure after the pivot means keep trying to finish, not try to undo everything.
Exactly. And those steps that come after the pivot are called retryable transactions.
Retryable. Makes sense.
These operations must be designed to be idempotent, meaning you can run them multiple times with the same result and fault tolerant. The system will keep retrying them until they succeed. This ensures that even if there are temporary glitches later on, the whole business process eventually reaches that final, consistent state promised after the pivot. Figuring out where that pivot point lies is maybe the most critical design choice.
Okay, so we've got the steps, the compensating actions, the pivot. Now, how do we actually manage the flow? Who tells service B to run after service A is done?
That's the next big architectural decision. It boils down to choreography versus orchestration. It's really a trade-off between how decoupled you want your services and how much explicit control you need over the workflow.
Choreography versus orchestration. Okay, let's start with choreography.
Right, choreography. I like the analogy of ants in a colony. There's no central director telling everyone what to do. Instead, services just react to events. Service A finishes its local transaction, and it publishes a domain event like order placed onto a message bus.
And other services are just listening for events they care about.
Exactly. Service B, inventory, hears order placed and reserves the stock. Service C, notifications, hears it and sends an email. They coordinate indirectly through events.
The big advantage there sounds like decoupling. Services don't need to know about each other directly.
Totally. Very loose coupling, high autonomy for each service, and there's no single orchestrator component that could fail. That's the upside.
Well, there's always a but.
The but is visibility and debugging. When you have lots of services just reacting to events, the overall business workflow becomes implicit. It's spread out everywhere. Trying to figure out why a specific order failed or where it got stuck can become incredibly difficult as the system grows. You're tracing events across multiple services, potentially leading to cycles. It can get messy, hard to see the whole picture.
Right, that sounds like it could get complicated fast. So the alternative is orchestration, taking back control.
Pretty much. Think air traffic control tower. In the orchestration model, you have a central component, the orchestrator, often called a Saga execution coordinator, or SEC. This SEC contains the explicit logic for the entire Saga workflow. It knows the sequence, step 1, then step 2, then step 3.
So it actively tells each service what to do.
Yes. The SEC sends a command to service A, process payment. It waits for the response. If it's successful, it sends a command to service B, update inventory. If service A fails, the SEC is responsible for triggering the necessary compensating actions.
So the failure logic is centralized too.
Correct. All the state management, the sequence logic, the error handling, it's all in one place, in the orchestrator.
That must make understanding and debugging the flow much, much easier.
Immensely easier, especially for complex sagas with many steps. The logic inside each individual microservice also becomes simpler. They just need to execute the command they receive and report back success or failure.
Okay, the downside.
Yeah.
It sounds like we've reintroduced a central component.
You have. The orchestrator itself becomes a potential single point of failure. If the SEC goes down, new sagas can't start, and ongoing ones might stall. So if you choose orchestration, you absolutely must build or use an SEC that is highly available and fault-tolerant itself. Using mature tools with built-in state management and retry capabilities is crucial here.
Let's make this more concrete. How do big companies actually implement these? Any examples?
Sure. Think about Uber. Their ride-hailing process is a classic example often cited for choreography. It's a very dynamic environment. A ride service might publish a rider-requested event. The driver service listens, finds a driver, and publishes driver signed. The notification service listens. It's all event-driven. Fits their need for high decoupling and reacting to real-time events.
Okay, dynamic, event-based. Choreography. What about orchestration?
Netflix is a great example there. They deal with complex but often well-defined internal workflows like encoding a new movie, setting up user accounts, managing subscriptions. They famously developed and open-sourced a tool called Conductor. Conductor is their Saga execution coordinator. It's a powerful orchestration engine.
So they define the workflows centrally in Conductor.
Exactly. They use a JSON-based language, a DSL, to define the steps, the inputs, the outputs, the error handling for these complex processes, all within Conductor. By using a robust, dedicated tool like Conductor, they get the benefits of orchestration clear workflow, easier debugging while mitigating the single point of failure risk because Conductor itself is designed to be scalable and resilient. For them, the clarity was worth managing a central component.
That makes sense. So the million-dollar question. When do you choose Saga, and when might you still need something like the old, stricter 2PC?
It really comes down to your business domain's tolerance for that temporary inconsistency we talked about. If you need massive scalability, high availability, and the business can handle data being briefly out of sync across services and e-commerce order processing, social media updates, then Saga and eventual consistency is almost always the right choice.
But what if you absolutely cannot tolerate any temporary inconsistency?
Then you might still need 2PC despite its drawbacks. The classic examples are core financial systems. Updating an actual bank account balance, for instance, or maybe managing critical limited inventory where showing the wrong count even for a second is disastrous. For those very specific high-stakes scenarios, the strict, immediate consistency of 2PC might be required, even if it means sacrificing some scalability.
So you're not saying 2PC is dead, just much more niche.
Absolutely. In fact, the most sophisticated architectures often use a hybrid strategy.
Hybrid, meaning using both.
Yes, use 2PC only for the absolute critical core, the financial ledger update maybe. That tiny part needs to be strongly consistent. But then you surround that core with Sagas for everything else related to the operations, sending confirmation emails, updating user profiles, notifying shipping partners, logging analytics. Those parts can tolerate eventual consistency.
That sounds sensible, but drawing that line, deciding what's core and needs 2PC versus what can be handled by a Saga, that must be tricky.
Oh, it's probably one of the hardest architectural decisions. Often, concepts like bounded contexts from domain-driven design help define those boundaries. Where does the strict consistency requirement absolutely end? The moment you cross that boundary, you're likely in Saga territory. It requires really deep understanding of the business domain and close collaboration between the business side and the engineers. Getting the pivot points and compensating actions right across those boundaries is crucial.
Okay, one more thing on Sagas. We mentioned the risk of temporary inconsistencies, things like lost updates or dirty reads, where one process reads data that another process is halfway through changing. How do we actively manage those risks? Just hoping for the best isn't enough, right?
Definitely not. You engineer defenses. There are several application-level patterns. One common one is the semantic lock.
Semantic lock, is that like a database lock?
No, not quite. It's done at the application layer. Think of it as a flag or a status marker on the data record itself. If Saga A is currently working on, say, inventory item 123, it sets a processing flag on that item's record. If another Saga, Saga B, comes along and wants to work on item 123, it sees the flag and knows to wait or handle it differently. It prevents two Sagas from stomping on each other's changes related to the same business entity, avoiding race conditions and lost updates.
Okay, so it's coordinating access at the business logic level.
Yeah.
What about dirty reads, reading incomplete data?
For that, a pattern like pessimistic view can help. This is more about structuring the Saga itself. The idea is to delay making the actual data modifications until as late as possible in the Saga. Ideally, you only commit the data changes after the pivot transaction has succeeded. This way, any service reading the data is likely to see either the old, stable state before the Saga committed or the new, fully consistent state after the Saga committed. You minimize the window where dirty intermediate data is visible.
Ah, I see. So it's about careful design within the Saga steps, too. That really highlights that eventual consistency isn't just accepting chaos. It's about carefully engineering how you manage the temporary states. All right, let's try to wrap this up. Key takeaways for our listeners.
Well, first, the Saga pattern is pretty much essential if you want resilience and scalability in microservices. You can't escape eventual consistency in most distributed systems.
And its success really depends on getting those compensating actions and, crucially, The pivot transaction defined correctly.
Absolutely. So, actionable advice. Number one, really understand your domain's consistency needs. Don't just assume Saga's always right or 2PC is always wrong. Know the requirements. Number two, plan your compensating actions from the start. Treat them like core business logic, not an afterthought you tack on if errors happen. And number three, if you go with orchestration, don't reinvent the wheel. Use mature, battle-tested tools like Netflix Conductor, AWS Step Functions, our Logic apps, whatever fits your stack. They handle a lot of the hard parts like state management and retries.
Good advice.
And one more thing, regardless of choreography or orchestration, invest heavily in observability. Good logging, metrics, and especially distributed tracing are absolutely vital. Without them, figuring out what went wrong in a complex asynchronous saga is nearly impossible.
Excellent point. Okay, so we've established that sagas mean embracing eventual consistency, designing for failure, which developers have learned to do. But let's leave our listeners with a final thought to consider. If the system underneath is only eventually consistent, meaning intermediate states will be inconsistent sometimes, even briefly, what does that mean for the person actually using the application? If I order 5 things, the order service finishes, but maybe the inventory saga part is still running. If I immediately refresh my order page, should I potentially see 0 items confirmed for a second? Or payment pending? Does the business need to think about building specific safeguards or different UI flows to handle those temporary glitches gracefully for the customer? Or can we really rely purely on those technical patterns like semantic locks and pessimistic view to hide all that complexity completely from the end user? Something to think about for your next distributed system design. We'll catch you on the next deep dive.